Okay, good afternoon, everybody. Thank you for the very nice introduction, Roos. And I hope that you are all inspired and amazed about the wonderful things that we can do with data science, because we had already some wonderful speakers here today. And of course, women that were speakers today. So yes, we can finally do that. Now, I will talk about today about that other central theme, which is the dark side of data science, which is bias in data science. Because whenever we build the day of today, our applications, our data science applications, we are more and more confronted. We are more and more conscious about that dark side, about that bias, about that discrimination in AI. And that's great, thanks. And by the way, when I talk about AI, for me it's the same as machine learning, it's the same as data science, it's the same as data mining. We just need from time to time a new word, because apparently we get more funding when we use new terms. Now the problem of today is that data science lately receives some criticism, because it has been proven with a couple of examples that data science is not neutral. I think you all know the example of the racist chatbot, right? Everybody is aware of the racist chatbot? Okay. I think we all know the example of the hiring system, the AI-driven hiring system that discriminates between genders. We all know about the juridical systems, the AI-driven juridical systems that discriminate between the races, right? Yeah, most of you know? Okay. The problem is that the day of today, the question is actually raised whether we can still use data science, whether we can still use data science to support our decisions, that we can still trust AI well enough to embed it in our day-to-day operations. And I'm a little bit surprised about that, because actually data science is a field where I strongly believe in. It's a field that I'm really convinced that it can enrich and augment our lives, but still it's now getting accused of something that is not because of data science. It's actually because of us, of humans, that AI is biased. And actually, it's now the time that it's up to us, all of us, the data science practitioners, to actually formulate why bias enters AI systems, to educate people on this, and also to come up with a solution. A solution together with the society, because believe me, data science will not be the only one that can bring a solution for this problem. Now, I hope that I can convince you today that it's actually the human in the loop that is responsible for creating bias in AI. And I also hope that I can reach a couple of solutions. I don't have a silver bullet, because we still need lots of research. So the same as Sophia, I'm going to ask you all to apply for a PhD and start researching this topic, because we still need research to solve this problem. But I hope that I can give you a couple of ideas where we can think about. So thank you for the clicker. So let's start with a couple of facts. So there exists an AI incident database, and the AI incident database is actually a database that reports on incidents caused by AI. And actually, the authors, they define an AI incident as a situation where AI systems caused or nearly caused real-world harm. Actually, yeah, our racist chatbot, our hiring system that discriminates against men and women, our juridical system that discriminates against races, they're all in there. But also AI systems that nearly caused harm, meaning systems that were recalled even before they were serving us, serving our society. Now, what we see is that more and more incidents are being reported. Now, before you start thinking, ooh, that's a bad thing, actually it's a good thing. Because now we can actually start learning from our mistakes. And let all the incidents that are part of this database, let them be an inspirational source. An inspirational source for all of us data scientists on how to not build AI. Because nobody, no organization wants to be on that list. Now, the question that I'm asking myself then is, how is it possible that AI systems that are so well trained, so thoroughly validated by professionals, by data scientists, by us? How is it possible that with all the best techniques in the world, we do not succeed in creating AI systems that are not biased? How is that possible? Well, for that, I went back to my school books. I'm still graduated as a data miner, not as a data scientist. But back in the days, I followed a course on data mining. And according to my school books, data science is set to discover patterns in data. More concretely, my lecturer defined it as the semi-automated process of exploring and analyzing large data sets to discover meaningful patterns. So data science is actually learning its logic based on data. Data created by us, by humans. So the discriminatory hiring system, it learned its logic, its hiring logic, based on past and biased data. Data coming from whom? Well, from us, from humans, from the recruiters that were previously advantaging men compared to women. The juridical system, the discriminatory juridical system, learned its sentencing logic based on data. Data coming from the police. Data coming from the police that were targeting one specific minority community. And you would think that we have learned our lesson. But no. Last year, here in the Netherlands, there was a big incident of families, thousands of families, that were accused of fraud. Accused of fraud by a model, a data science model. Why? Because a data science model used data from the police, again, by over-policing a specific minority group. Now, before you think, it's the data. Data is the source of all evil. It's indeed true, data is not neutral. But don't be misled. Algorithms are also not neutral. Same as decisions. Decisions that are based on the models that we build are also not neutral. And let me explain that to you. So, data is not neutral. Okay, so the recruitment data, that's an obvious case, but I would like to show you an example that with even innocent data, or seemingly innocent data, we can also do some harm. And for that, I have here a very famous psychological experiment. The psychological experiment actually asks the people to count the number of times the people with a white t-shirt, how many times they pass a ball to each other. Yeah? So I will start the movie. You will all start counting how many times the people with the white t-shirt are passing the ball. Great, such a concentrated audience. So, what's the answer? How many times did they pass the ball? 14, 15? It's actually 15, but that's okay. But, did you see the monkey? Okay. That's weird because normally when you see it the first time you don't see the monkey, but okay, that's good. Now, I also applied an object detection model to this movie. I applied an object detection model again to also count the number of times the players in white are passing the basketball to each other. What do you think? Oh yeah, and I trained the model, maybe it's good to have some details. So I trained the YOLO model based on the coconut dataset. And the coconut dataset is a dataset with lots of images with a large variety of different classes, like people, bicycles, cars, and trucks. What do you think? Do you think my algorithm was able to count the number of times people were passing the ball? Somebody cannot, like yes or no? No? Okay, no. And what do you think? Do you think my algorithm or my model saw the monkey? No? Okay, let's have a look. So for the people who didn't see the monkey, they will now have the chance to see it. Here it is, entering the screen. Very obvious in the middle of the screen. And going out. Now I hope that you realize that my object detection model failed. It failed in any sense because it failed to detect the basketball. So I couldn't count the number of passes that were given. It also failed to identify the monkey. Even worse, it identified the monkey as a person. Now having a closer look at that data set, that coconut data set, it's actually normal that it cannot do the task for which, or what I asked from it. Because basketball was not part of my data set. Monkey, and I highlighted here the animals, was also not part of the data set. So it's very important to realize if it's not in the data, it will not be in the model. My model will not know it. And you might think, oh, this might be a funny example, just not good enough to put it in the AI incident database. But if we put such AI systems in real life, in practice, it can quickly go wrong. And actually, there was an incident a couple of years ago. Of course, it was the complete opposite way, where black people were labeled as monkeys. And this is, of course, something that we want to avoid all times. Now, just before you think, okay, it's because monkey was not in the data set, it's because basketball is not in the data set. Well, the problem is a little bit more complex than at first sight. Because when we have a look at the origin of the images from the coconut data set, but also other open image data sets like ImageNet and Open Images, and we compare this with the geographical distribution of the world population, we actually see that in those open image data sets, Western countries, our countries, are overrepresented. This compared to countries like Asia, countries from Asia, or from Africa or South America, they're underrepresented because those people have, in a lesser extent, access to the internet as us. Now, this is a problem of data diversity, and this can be a huge problem because objects that might be, or images that might be available in the data set, might be completely wrongly classified by the models that we build. For example, if we want to classify soap or we want to classify kitchen herbs, if we take a picture from a Western country, our computer vision models will do a good job. But when we apply that logic to Asian, African, South American countries, our object detection model will fail. Oh, sorry. So just as with the GIGO principle, garbage in is garbage out, we should actually think about the BIBO principle in data science. Bias in is bias out. And it's not only about data availability, it's also about data diversity. So what should we do? How can we solve that? How can we solve this data neutrality problem? Should we actually train machine learning models based on our biased society? Or should we actually use data that is coming from a society of equity, actually artificially generating data and losing all the imperfections of our society? Or should we use our natural data sets, full of social biases? Well, actually, it's a choice that we have to make between, or not a choice, but it's something that we have to think about a laissez-faire data collection strategy, where we use indeed these natural data sets with their social biases. And it's easy because they're just readily available. Now, at the other side of the spectrum, we have the interventionist data collection strategies, where we carefully select what data we would like to use. Now, don't be naive. Also, those data collectors have their own political biases. They can also include some political and topical biases, but it requires time and effort. Now, Probably because data bias, it's a misrepresentation and incompleteness of examples. Probably the solution is somewhere in the middle. Natural data sets are far from ideal. But if we, data scientists, are at least a little bit conscious, and we think a little bit about those data collection strategies, about how we can improve bias in our data, it will be a first step in making data more neutral. Second part, algorithms are not neutral. A couple of years ago, there was again a big incident with credit cards and credit card limits, and apparently there was an AI algorithm behind the scenes that was discriminating between men and women. So I followed the case a little bit. The case came out, and one of the journalists was interviewing the representatives of the company, and the representative said, well, we swear that we are not discriminating. It's just the algorithm. It's just the algorithm that is discriminating. This is something that we cannot do, right? And again, it surprises me because, again, people are hiding behind algorithms, while it's actually, again, the human in the loop that is a problem. And I agree here that it's also more a data problem. But don't be naive. Also, algorithms can be biased. And for that, we use the term algorithmic bias. And algorithmic bias is actually a bias that is not present in the input data, but is purely introduced by an algorithm. And for that, I want to go back to the definition of data science. I remember that data science is finding, discovering patterns in large data. Now, I'm a young mother. I have a little son of 1 year and a half. And he looks nothing like me. So he's a complete copy of my husband. He actually has exactly the same interests. He is really excited about techniques, about engineering. And what he really likes are wind turbines. But yeah, we don't have any wind turbines in the neighborhood. Only thing that we have is a baby book with a wind turbine. And me and my husband, we connected it to this Dublo block, yeah, the wind turbine of the Dublo. By the way, I have one important task today, and that's not to lose this block, because otherwise my little son is going to be very mad. Now, that's the only thing that he has. He never saw real wind turbines. Now, a couple of weeks ago, we were driving by car, because we can now go out, all of us, after Corona, after COVID. And we were passing by a park of wind turbines. And you know what? He made the connection. He made the connection with real wind turbines and the little Dublo block or the baby book. Now, why am I telling you that? Because, of course, I'm a very proud mom, but also because that's something that at this moment we cannot expect from AI systems. If we only provide one example to AI systems, they will get confused. And if there is something that we don't want that algorithms are, it is that they are confused. So in order to avoid this confusion, we want to limit the noise in our data. And for that, we have to balance between bias and variance. One technical slide. The bias-variance trade-off actually means that we have to balance between high-variance models. Models that are oversensitive to noise and small fluctuations. Actually, we call it overfitting. And actually, as data scientists, we are trained to make models generalizable, to avoid overfitting, to avoid that our model reacts to every noise. The other side of the spectrum are high-biased models. Models that are unable to find a relationship between inputs and outputs. This is what we call underfitting. So the red dashed line is an underfitted model. Now this comes with a danger, because if we reduce noise in such a way that we do not find specific patterns in data, like this drop, okay, this might be perfect if it's noise or outliers, but what if this drop represents a minority group? And that's exactly the problem with those algorithms, and by underfitting those algorithms, because people with unusual tastes, unusual preferences, unusual characteristics, they're actually mistreated by the models. So, and this is my call to you, dear data scientists, please know the algorithm's assumptions and limitations. And I know here, in this group, that we are all of goodwill, and it's actually easier said than done, because how can we actually start tackling these problems if we don't know if we are biasing? What should we do about this? And I know that there are many criteria that we can use, fairness assessment criteria, on group level, like the equalized odds, the equal opportunity, the demographic parity, or on individual level, where we can check on fairness through awareness, or fairness through unawareness, or counterfactual fairness. The problem is that those assessment criteria, they lack one thing. They don't tell us if we are biased or if we're not biased. They just tell us how biased we are. They just tell us, you're 70% fair. What should we do? Now, let me make that a little bit concrete, and let's start with this example. This is a selection rate for an event per group, for, let's say, to get hired. And according to this graph, 30% of the Italians in my data set are getting hired, according to my model, compared to, let's say, around 50% of the Greeks that are getting hired, according to my model. So a difference of 20%. What do you think? Is it fair or not? Fair or not? Nobody dares to answer. Not fair? I agree that it's not really fair, but you see that we have a problem. And the problem is that at this stage, we don't have any regulation. We don't have any legislation that says this is fair or this is not fair, because fair for me might mean something completely different than fair for Fleur, for example. Now, the only thing that we have available the day of today are rules of thumb, like the 4/5 rule. And the 4/5 rule actually says that the selection rate of any group in your data set cannot be less than 4/5 or 80% of the group with the highest selection rate. What does that mean? Well, suppose that my yellows have the highest selection rate to get hired. 60% of the yellows are getting hired. This compared to the purples, a group where only 30% gets hired. Well, the selection rate of my purples represent 50% of the selection rate of the yellows. 50%, less than 80%. So actually here we say that my model is not fair. What we can do is we can increase the number of hires from my purple group. In this case now, if we increase it to 50%, my purples, the selection rate of my purples, represent 83% of the selection rate of my yellows. And in this case, we say that it's a fair model. So, suppose on my example, I'm applying here the 4/5 rule. What do you think? Is my model fair now? Yes? Other opinions? So I'm here in I'm talking here in the Netherlands. What about the Dutch? What about the Dutch? What about the Belgians? I have to say my nationality as well. And I know that there are other nationalities here as well who are not represented in this graph. What about those groups? And this is what we call the blind spots, and these are even more dangerous, because how can we know the unknown? And actually, I was hoping a little bit that here somebody would say, hey, the Dutch are not in the graph. But actually, when you are part of this group, this minority group, this group that is not treated according to the model, you are a little bit, you're in an advantageous position, because you see things that other people do not see. So as an organization, what we can do, and I heard already a couple of speakers talk about that they have diverse teams, and this is indeed one step in the right direction. Having diverse teams is one step in the right direction of making algorithms more neutral. Okay, last part, almost finished. Decisions are not neutral. Decisions that we make based on our data science models. And this highly relates to interpretation bias. Interpretation bias is bias that is introduced by humans by inappropriately interpreting and or using machine learning logic. Now, what can we expect from a machine learning algorithm? Let's all be honest. A machine learning algorithm or an AI model or a data science model always returns a probability. I know that there are statistical thresholds, but it always returns a probability. For example, in fraud detection, my domain, it returns a 55% probability that your credit card transaction might be fraudulent. In customer retention, it might return a 75% probability that your customer might churn, might go to the competition. In epilepsy prediction, it might say that there is a 25% probability that my patient gets a seizure. In predictive maintenance, it might say that there is a 51% probability that my machine will fail. But what does that mean? Does that mean that my credit card transaction is fraud? Does that mean that my customer will churn? Does that mean that my patient is going to have a seizure? Does that mean that my machine is going to fail? And if there is one thing that we as humans are not good in, it is interpreting statistics. And I call it statistical missensitivity. Actually, the statistical mismatch about what a machine tries to tell the end user and how the end user absorbs these statistics. And it is proven that end users trust machine learning models a lot as long as they ask a lot of questions, as long as we have a lot of features included in the AI systems. It's also proven that sample size, we don't care about that. If the probability is based on 100 or 1,000 or 10,000 observations, we don't care. And it's also shown that when an AI system or an AI model asks for input that we cannot provide, so we have to input missing values, we have to input uncertainty, that our end users are really distrusting our machine learning models. Now, due to this statistical missensitivity, there is a big danger. It's what is called the extrapolation danger, which is actually using a model outside of its intended context. Going back as a proud mother to my son, I remember, he's really into techniques, and he really loves, next to wind turbines, airplanes. So whenever an airplane flies over, he's pointing to it, but also we connected it to his baby book. A couple of months ago, I thought, how well would a computer vision model perform? So I gave a computer vision model a picture of one of the airplanes, and you can see that with a high confidence, 96%, my computer vision model correctly classified the airplane. Then I took a picture of the baby book, the full page picture. But in the full page picture, it was too confusing. There were too many objects on it, so it didn't work. So what I did was, I zoomed into the airplane. That's the airplane. And my computer vision algorithm labeled it as a shark, with a 67% confidence. It's actually the same as with the monkey example before. And that's actually a big issue, because a machine learning algorithm, like I said before, will always return a probability. It will always try to do its best, even if it's not trained to perform this kind of task, because this computer vision model was not trained on baby books. So this extrapolation danger actually means that we're going to train a model based on a limited data set, and we're going to apply the model outside of its intended context. And this can, of course, have very drastic consequences if the truth is completely different. Now, while I was preparing for this presentation, I was actually thinking, how can we solve that? Because it's quite hard to solve this. Well, we have a division at SAS, which are the credit risk modelers. And for the people who are aware of that, credit risk is a domain that is highly regulated. Actually, they already apply these kind of techniques for more than 20 years. And what they told me is that in credit risk, you're obliged to work with the so-called model risk cards. Model risk cards that actually document your model. They document standard things like the project scope, the business objectives, the risk assessment, the materiality, but also the intended use. And more importantly, it's not a one-off exercise. This intended use, these model characteristics, are continuously monitored over time. So again, what can we do about decisions that are not neutral? I don't have a silver bullet, but working with a good documentation, maybe borrowing some techniques from risk, like the model risk cards, might be a first step to make decisions more neutral. So I hope that I have convinced you that data is not neutral, because data is created by humans. That algorithms are not neutral, because it's us, data scientists, that use these algorithms. And that decisions are also not neutral, because it's us, humans, that make a decision based on the models. But I hope that I also have convinced you that we can do something about it, and that actually it's time now to do something about it. Thank you very much.